let's see. So a couple things. We didn't win this weekend. I told my wife I had this morning. We are going to state, or one of our kids is going to state. So we won't have class on March 11th. So if you're one of our kids today, that's on Friday. We're not supposed to be here all day. So sorry for that. That's simply this. We have no class on March 11th. Okay? But y'all your weekend? Understand it's a busy week for y'all, for some of you anyway, a lot of exams, some of you. Yeah, I'm sorry for that. Some weeks are not face. But we will have an exam in this class on Friday. We will also on Wednesday have that aeration. When you come into class, let's see. Where would you rather have the beginning or the end of class? The beginning. Beginning of class. We'll do it. So we'll have like 10 minutes or so, and you can do the derivation, and then we'll start the class right after that. We will have some time for review on Wednesday. We're going to do a little bit more work on the capacitor circuit, but otherwise we'll go to chapter 2. But that exam will cover 0.5, Gauss's law, electric potential, electric fields in the context of finding the potential function like we did with partial derivatives. We'll go over that on Wednesday, but all chapter circuits. Okay? Capacitor circuits as well. You can see two capacitor circuits. You can see one that's centroid and one that's not. Okay? Want to do another practice problem for capacitor circuits? I think some of your kids are going to do that. But make sure that you're not by Friday because you will see one. Let's see, this one is in the back of your book. It's on the old exam. Page 305. So here, yours will look something like this. It'll be different but similar. We have like 5 capacitors. We want to find the equivalent capacitance, the potential, and the charge on each of the 5 capacitors, and then also as for the energy stored on the 2 microfarad C5 right here. So again, as I said last time, you'll have one of those questions just tucked away somewhere within a question. You're not going to have a separate energy problem. Equations are on the sheet. On the equation sheet, it's 1/2 CV squared. There's some other expressions to find it, but just know where those are and how to find it. So first thing, we just want to find the equivalent capacitance. And actually, your first step here might be to redraw the circuit. And there's been some question about, I think it's probably more apparent here, but how to find when capacitors are in parallel or in series. So we're going to come along here, we'll trace along to our first junction. So starting on the big side of the battery, come along to our first junction, and then that represents where our first branch splits off. So this is our first parallel branch. Notice that this just splits into 2 branches before I get to my capacitors, right? So I have one going here to my first capacitor and then one going here to my second capacitor. And so I'm going to have this as a parallel branch. And then I come along here and notice that this top branch, I'll redraw this in just a second, but the top branch here will split off into 2 additional branches. So I'm going to have an initial branching into 2, and then on the top one, another branching into 2. And then they all come back together right here, and they go back to the battery. We did one that was pretty similar to this. That was really similar. I think it wasn't the same one, was it? I'm pretty sure it wasn't. But let's see. So if I redraw this, I have my 12 volt. This is my 6 microfarad. I have my 2 branches up here. That's coming right here. 1 branch, 2 branches. This is 4 and 1. And then up here, I split again here and here. And I have a 2 and a 2. And they come together. All of this comes back together, and they go to the battery. Hold on, let me check something. This was, you might know which exam this is. surprised I would have given you those numbers. They sort of come out funky. Huh? Which exam is it? Is it spring what? 15? Let me just look online, make sure that is the right numbers. I'm not sure what the deal is. I'll have to look into it. Okay, well, let's just go with that. So here, I want to, on my equivalent, I'm going to have a 4, and what do these two add up to? A 2 and 2 in parallel is also going to be 4. So let's change, actually. I'm going to change C2 to 2 microfarads. I'm sorry. So that will give me a 2 and a 4 is 6, and then I'll change this to a 3 microfarad. It'll make the math a little easier. Yeah, I think that'll work better. So now if I have a 2 and a 4 up top, what's the equivalent there? So remember, this 2 plus 2 up here becomes equal to 4. If I have a 2 up, if I combine that with a 2 microfarad, oh shoot, I'm sorry guys, this isn't working right. Let's go back a second. Hold on, I'm sorry. We're going to go back to the original numbers. Let me think for just a second. So if I have an 8 and a 1, that would be 9, and then our 6. Okay, that'll be fine. Let's go with that. I'm sorry. So we'll go back to the numbers as they're on the exam. So what is going to be my equivalent of this top branch right here? What is it? It's not. I have a 4 and a 4, right? So that's going to give me a 4 and a 4 in the series, which is going to be 2. So these combine here to give me 4 microfarads, and then these combine here, a 4 and a 4 in series. That's 1 over a quarter plus a quarter, which is equal to 2. So that gives me a 2 microfarads. I can go ahead and redraw that. I have my 6 microfarad here, and then I have a 2 and a 1. Two microfarads, 1 microfarad, and then those two will combine to give me what? 3. So I'll combine those to give me a 6 and a 3. And then of course those two will combine to give me what? A 2, right. So 1 over 6 plus a third is equal to 2. So my equivalent capacitance here is 2 microfarads. I have 12 volts here. And now we want to start stepping back. So I always find it helpful to draw my intermediate circuits, because then it allows me to find those voltages more easily, because you can see sort of where this capacitor is the equivalent of these two capacitors, and then you can see those voltages and how they're separated more evenly. So over here on the 6 and the 3, I have 12 volts. Remember, there are a couple ways you can do this. You can find the equivalent capacitance, which we've already said is 2 microfarads. 1 over a 6 plus a third is equal to 2. If the equivalent capacitance is 2 microfarads, that means the charge on that equivalent capacitance is 2 times 12, or 24 microcoulombs. So each of these capacitors has 24 microcoulombs of charge. Because capacitors in series have the same charge, so if they both have 24 microcoulombs, then I can find the voltage. Voltage is Q over C. or Q is CV, so V is, yeah, Q divided by C. So it's going to be 24 divided by 6, 24 divided by 3. 4 volts, 8 volts. But we can see how they're distributed too, because we know that the big capacitor has the smaller voltage. The smaller capacitor has the bigger voltage by a factor of 2. So this has to be 4 volts, this has to be 8 volts. You'll have common numbers like that easy to see. So if you're familiar with them, this will be 4 volts. You shouldn't have to go through that whole argument with the charge, finding the charge on the capacitors. Okay? But you should know how to do that nonetheless. That you first, if you find the charge on the capacitors in series, on the equivalent capacitance in those series, then you'll be able to find the voltages on them, because they'll both have the same charge. Capacitors in series have the same charge. Alright, so now that I have these voltages, what's the voltage across the 6 microfarad capacitor? This is going to be 4 volts. And then across the 2 microfarad capacitor, 8 volts. 8 volts. Because this capacitor is 8 volts. This capacitor is the equivalent of these two, which are in parallel. Capacitors in parallel have the same voltage, and they have the same voltage as their equivalent capacitors. So I have 8 volts here, I have 8 volts there, and there. I have 8 volts, 8 volts, 4 volts. Now I can step back again, recognizing that this capacitor is the same as this capacitor. So I have 8 volts here. Here I have a 4 and a 4 microfarad capacitor. 2 identical capacitors in series. Across their equivalent, they have 8 volts. So what must be the voltage across this capacitor? It has to be 4 volts. 2 identical capacitors in series will split the voltage equally, only because they're identical capacitors. They have the same charge because they're in series, and the same voltage because they're identical capacitors. So I'm going to have 8 volts across this whole thing, so I'm going to have 4 volts across that 4 microfarad capacitor. So I have 4 volts here, and then, final step, I have these 2 microfarad capacitors. I know that across that parallel branch, I have 4 volts. What is going to be the voltage across this 2 microfarad capacitor? It's going to be 4 volts, because capacitors in parallel have the same voltage. So whatever the equivalent capacitance, which for these 2 microfarad was a 4 microfarad capacitor. We didn't draw that, but these two have a 4 microfarad equivalent, which has 4 volts. Because these are in parallel, they'll have the same voltage as their equivalent. So I have 4 volts and 4 volts. So I have 4 volts here and 4 volts here. And then it's just a matter of writing it down. So C1 was the 6 microfarad right here. That had 4 volts. C2 was this 4 microfarad. That's this one. It had 4 volts. Or did they all have 4 volts? No. C4 and 5 both have 4 volts. That's these 2 capacitors right here. This was C3, is this 1 microfarad. It's right here. It has 8 volts. And then once you find all the voltages, you just go back through and you say Q equals CV. Q1 is C1 V1. C1 was 6 microfarads, so it's going to be 6 times 4 or 24 microcoulombs. And then you can do the rest for the others. Okay, we have C2 is 4, so 4 times 4 is 16. C3 is 1. 1 times 8 is 8. C4 and 5 are both 2, so these will both be 8. Just to be complete, let's see, this is 8 microcoulombs, 8 microcoulombs. What was 2? What did I say 2 was? 16. And Q3, 8. Yeah. And then again, the energy here, E5, is just energy is 1/2 C5 V5 squared. It's going to be 1/2 of 2 microfarads times V5, which is 4 volts squared. So that's 16 microjoules. Make sure you get the micro there. It's not in joules, it's in microjoules. Or it could be 1.6 times 10 to the minus 5 joules. All right, let's look at one other problem on some of the other old tests. I would recommend that you go through, there's one in the homework, go through too and look at some of these. There was one, Stephen, do you remember where that was with the one that was diagonal? Spring 14, probably exam 2. Oh yeah, let's look at this one. This one looks a little bit different, but I want to, you could see something like this, where you have this one capacitor sort of drawn off on a diagonal. But in general, with circuits, I can move a portion of a circuit anywhere along a branch, as long as I don't cross a junction or I don't cross another device, like a capacitor or resistor. So for example, I could redraw this circuit to look, instead of like this, I could redraw it to look like this. And then it looks a lot like one that we've done before. I could draw it other ways too, right? I could draw it to look like this if I wanted, as long as I don't cross a junction or as long as I don't cross a another device. So for example, I could not draw it where C5 is like this. That would not be appropriate because I would have crossed a junction at this point. And I also could not draw it, get rid of all this. I'm going to redraw the whole circuit in just a second. I also could not redraw it like this because then I would have taken this portion of the circuit and crossed over C2. So I can't cross over a junction and I can't cross over another device. But it would be perfectly fine for me to redraw this circuit in this way, where I have the capacitor not on a diagonal like that, but just, you know, in a grid like we've been doing. So if I do that, I can redraw my circuit to look like this. I can have my battery, starting with my battery, coming off the big side. I come over here, I find a junction. That junction has 2 branches. By the way, if I wanted to have a third branch, well, hold on, I'll show you that in just a bit. For right now, I have 2 branches. I'll call this one C3. It's 6 microfarads. Down here, I have C1. It's 4 microfarads. Why don't you try finishing up the circuit here? So I've already got to this point. Now you need to go along. Notice that you have another junction right here. You have another capacitor coming along here. And then try to take that back to the battery and see what it does. I'll give you just a minute. Try to redraw that circuit. Alright, so after my 6, or rather after my 4 microfarad capacitor, what's the next thing to come? After this capacitor, which I've drawn right here, what's the next thing that's going to come? We're going to get another 4, because as I come along here, I hit another 4, and then I go along until I come back to this junction. So I'm going to hit another 4 microfarad capacitor here. And now let's deal with the top circuit. After I draw the 6 microfarad capacitor, I come along here and I hit another junction. So I have to draw another parallel circuit, or another parallel branch. In this top branch, it'll look like this. That's going to be a 1 and a 2, a 1 microfarad and a 2 microfarad. And then from there, everything comes back together. And it goes back to the battery. So that's what my circuit looks like. That one is actually not a terribly difficult circuit. If you notice, I have a 6 and a 3, gives me 2. I have a 4 and a 4, which gives me what? 2. So I have a 2 and a 2, which is going to be an equivalent of, what's my equivalent of that circuit? 4 microfarads. They're all numbers that we've seen before, so let's just step through and find the voltages. Again, I have 4 and 4, which is 2 microfarads, 1 and 2, which is 3 microfarads. So if I redraw that circuit, it looks like this. A 6, a 3, a 2, then if I combine the 6 and the 3 right here, that gives me 2 microfarads, and then the 2 and the 2 is 4 microfarads. So my equivalent here is 4 microfarads. Now I have 12 volts here. That means I have 12 volts here, 12 volts. I have 12 volts across the 6 and the 3. So across the 6, I have how many volts? Remember, they have to add up to 12. I'm going to have 8 and 4. The 6 microfarad will have the bigger or the smaller of those? It's going to have the 4, right. So the 6 will have the smaller of those, which is going to be 4 volts. So I have 4 volts here, 8 volts here. I have 12 volts here. Notice that this 2 microfarad capacitor is actually made up of these two 4 microfarad capacitors. So each of these, I have 12 across the whole thing. So across this 4 microfarad capacitor, I have 6. Because they're identical capacitors, they will split that voltage evenly. So I have 6 volts and 6 volts. Let's see, I've already said that I have 4 volts up here. Across both of these, I have 8 volts. So what is the voltage across the 1 microfarad capacitor? It's 8 volts, as well as 8 volts there because they're in parallel. And then we just need to transfer those to the table. So let's see, C1 is the 4 microfarad, that was 6 volts. C2 is that other 4 microfarad, that's 6 volts. C3 is the 6 microfarad, that was 4 volts. And C4 is the 1, that's 8 volts. And C5 is the 2, that's also 8 volts. And then we can find the charges on each of those. Okay? You'll have a very similar circuit to that. It'll be, you know, that or maybe another capacitor or two, but very similar. And you'll see a lot of the same combinations that we've seen. The 4 and the 4, the 3 and the 6, the 2 and the 2, the 3, 6, and the 2 all in series. We have that one. That's all added up to equal to 1. So the numbers should work out fairly simply too, as it does in this one. Okay? Learning to do these circuits will help you in the next chapter when we get into resistor circuits as well. We have a lot of time in circuits, so in the rest of this class, so it'll be good to sort of master this right now. Y'all feel like you've mastered capacitor circuits? Some of you? Okay. It will definitely be on the exam on Friday, so if you haven't, spend some time this week really digging into those, and if you need help, I'm available. If you have questions on Wednesday, we'll readdress them on Wednesday. But for now, I think we're going to move on, if that's okay, unless there are any burning questions about capacitors. It's kind of important because, like I said, we're going to spend a lot of time in circuits, and just being able to interpret circuits will help you for the rest of the class. All right, I'm going to clear this out. All right, let's start. Oh, did we finish? We did finish the concept test, right, for chapter 2? Yeah, we are going to move on to chapter 3. But as I said, Chapter 3 will not be on the exam. Um, let me just run through the homework right quick. You'll have this problem on Wednesday. Make that clear at the beginning of class. That's number 11 in the homework. So if you don't have it in your notes, you can look back in the homework and find the solution to that. I'm going to want to see that. I want you to spit it up onto the paper, okay? I just want you to memorize it. I understand that you'll probably forget it halfway through the day, but that practice is useful just to memorize something and or even better, just think about the process. And then there aren't that many steps, really, and the steps are pretty simple, so just think about the process of it. You will have a question like this on the exam. You might have two, where one is a little bit simpler, like for example, series or parallel or something like that. The geometry of capacitors, you'll likely see that. Finding the potential through, or the electric field through a potential function. Finding the potential due to a collection of charges. Remember, they're not vectors, they're scalars. Finding the electric potential energy of a collection of charges too. You're going to see probably all of this stuff. So, and then also finding the velocity, the work energy theorem. When we cross potential, we get that charge kinetic energy. We work with problem like that first in the first part of the chapter. Okay, chapter 3 is a big chapter, a lot of stuff in it, but you'll probably see all or most of it on the exam. Make sure you go through the homework. They're very similar to things that you'll have on the test. All right, chapter 3 is a pretty short chapter. In fact, we might even finish it if we, depending on sort of how much time we spend on review, which, depends on how many questions y'all have. We could finish it on Wednesday. But as I said, it dovetails nicely with chapter 4, so we won't put it on the exam. Unless y'all really want it on the exam, do you? Yeah, probably not a good idea. So let's just keep chapter 3 on the next exam. But let's go ahead and define some of these things. Current, which we haven't dealt with yet. Even though we've dealt with circuits a lot, the capacitor circuits have had no current in them because we've always assumed that they've been in equilibrium, that they've had some time to equilibrate with the batteries. Now, in a capacitor circuit, there is current that flows, but it only flows at the very beginning when you first start charging those capacitors. After you get the capacitors charged, there's no more current that flows. Now, later in chapter 4, we'll deal with the charging and discharging of capacitors, which is really what makes them useful. How you discharge a capacitor can help you to build circuits that have a particular time in them. All right, so anyway, current is the rate at which charge flows. Past the point in a given time. It's a rate. Just like velocity is a rate, just like acceleration is a rate of change of velocity. We're going to define current as Q over delta T, or usually actually current is defined with a small q, but either way is fine. The unit for current is an ampere. This is often defined, or it's abbreviated in a couple different ways. You might see it as a capital A, that's how we'll do it. You also might see it sometimes as an amp, like that. You might see that on your electrical devices. Often on your electrical devices, they'll give the operating current, which is based on the power that they consume. 1 amp, and this is equivalent to 1 coulomb per second. Because it is a charge over time. Charge is in coulombs, time is in seconds. In fact, we'll see later that the coulomb is actually defined by the current. We'll see that, I think it's in the next chapter, how that is actually defined. It might be chapter 5. We have a conventional direction of current, and we've sort of seen this as I've been drawing the circuits. I always start at the positive side of the battery, and you might have wondered why we start at the positive side instead of the negative side. Or maybe you didn't wonder at all. I'm not sure. Did you wonder? Well, we always start at the positive side of the battery because the direction of conventional current flows from the positive side to the negative side. So conventional current flows not as electrons would flow, but as protons would flow. Notice if I had electrons, electrons move from, anyway, electrons would move in this direction. But instead, we're looking at the flow of protons, which are in this direction. This is just because of Benjamin Franklin, that we have this convention that's not really physical. Because Benjamin Franklin used to think that, Benjamin Franklin, who did a lot of pioneering work for what we know about the use of electricity today in circuits, he thought that protons were actually flowing in the circuit. Because, the atomic model didn't come until, gosh, what, the 1800s or so? Like, we haven't really understood atoms in the way that we understand them now for not that long, really, couple hundred years or so. So the idea that, so Ben Franklin thought these positive charges were flowing, not negative charges. He understood the difference between positive and negative charges, but he thought that they were protons flowing. And of course, we know that that's not the case, right? Because the protons are tightly bound in the nucleus. And it's only those electrons, those conduction electrons, which are allowed to flow through the circuit. All right. Positive charges are repelled by the positive terminal and attracted to the negative terminal. That's how I remember it. What is the conventional flow? If I imagine my circuit like this, the positive charge is repelled from that side and they're attracted to the negative side. I know that y'all did ammeters and voltmeters in lab, or I think that some of you missed out that lab when we had the bad weather. But you will have a little bit of that in this class. You just need to know the basics of what a voltmeter and an ammeter are and how to hook them up. Even if you missed the voltmeter ammeter lab, you should just still have gotten that in the lab. So anyway, in a circuit, one uses an ammeter to measure the current. And in general, when you measure things, or rather the ammeter is hooked up in series with the resistor. So here, for example, if I have this circuit and I want to know what is the current in this resistor, then in order to find that current, I would put an ammeter in the circuit. So I would physically unhook the wires and attach them to the ammeter so that your current would flow through the ammeter and then through the resistor. So our ammeter is hooked up in series. We're going to have our ammeter and then we'll have our resistor. In general, when you measure things, you want to not change the thing that you're measuring, and that can be actually quite difficult. But the ammeter is hooked up in such a way that it doesn't change the actual circuit. What would the resistance of the ammeter need to be in order to not change the circuit? Would the resistance have to be really, really big or really, really small for the ammeter? If you're going to hook it up in series, does it need to have a really, really big resistance or a really, really small resistance to not affect the circuit at all? It needs to have a really, really small resistance, right? Because if it had a big resistance, the charges coming on here, they would see that, and say, oh, there's a really big resistance there, and then you'd get a very small current. Ohm's law, we'll get to that in just a bit. But you'd get a really small current. So if you had a big resistance in that ammeter, it would affect the circuit. So the ammeter of your resistance is really, really small. So as to not affect the circuit. Because if you affect the circuit, then what's the point? If by the act of measuring you actually change the circuit and change the current, then you've really not done a very good job. In general, that's a difficult task, to measure something without changing it. Actually, if you look in the back of your ammeter, in the lab, you have those analog ammeters, which are pretty nice actually. They make digital ammeters that you can buy at Radio Shack or wherever that are multimeters that measure both current and voltage. But the analog ones upstairs, you can see in the back, there's a little coil of wire. That coil of wire is your resistance for the ammeter. So an ammeter has a very, very small resistance. A piece of wire has a very, very small resistance as well. It's kind of like your capacitor meter. It has a very, very small resistance too. It's just a coil of wire. All right, let's look at voltmeters. To measure the voltage in a circuit, use a voltmeter. And the voltmeter is going to be hooked up in parallel. Remember how we talked about when we measure the current, we measure the current through something, how the current flows through the resistor, but you measure the voltage across or between 2 points. Okay, so when you hook up your voltmeter, you're going to hook it up to 2 points and measure the potential difference or the voltage across those 2 points. So if we want to know the voltage across this resistor, we'll hook up our voltmeter like this. So our voltmeter will be hooked up in parallel. Now, what do you think the resistance of the voltmeter, is it going to be big or small? It's going to be very, very large actually. Do y'all know what the resistance in the voltmeter is called? Y'all remember this from the lab? In the multimeter, in the ammeter, that resistor in the ammeter, you have a galvanometer. We'll talk about in chapter 5 with its magnetic field. We have a galvanometer, and then you have a multiplier resistor. Do you remember in the voltmeter what the resistor was called? The shunt resistor. Yeah, that's kind of cool to say, isn't it? Like, y'all like this shunt. Y'all want to say it with me? Right. Go ahead. It's sort of the sound. I don't know. Shunt. The shunt resistance. This is called a shunt resistance. You don't need to know that, but it is really, really big. You can imagine that if I have charges that are flowing through here, and if I have a very big resistor, these charges are going to come in, and in general, current will take the path of least resistance. That's where that phrase comes from, actually. To take the path of least resistance actually is referring to charges, that they will take that path of least resistance. And so the charges are going to come here, and they're going to say, which direction should I go? Should I go through this really big resistance and lose a whole lot of energy? Or should I go through this little bitty resistor and lose like no energy at all? So they're going to go instead through the smaller of the resistors. So the shunt resistor is huge. It's like 10, 20, 30,000 ohms. It needs to be a lot bigger than your actual resistor that you're measuring across. All right, so the voltmeter has a big resistance. Very little current flows through it. Because that resistance is so big. All right, let's try this quick test. You probably have a multiple choice question or two about voltmeters and ammeters on exam 3, which is, several weeks away. If you wish to measure the voltage across a resistor, you should connect the measuring device in which way? In parallel, in series, replace the resistor with the measuring device, or does it depend on the circuit? All right, I'll stop at 38. Okay, awesome. A is right. It wasn't quite 90%, but I have a good joke for you, because you chemists will like this. You ready? You're going to be telling this like all day. It's hilarious. What do you do when a chemist dies? You bury him. You did it, bury him. Okay. So yeah, what was the answer? In parallel. A is the right answer. Which of these statements is always true? Current through an ammeter is small, the current through a voltmeter is small, the voltage across an ammeter is small, or the voltage across a voltmeter is small. This one's a little more difficult, but think about how we measure current and voltage and what that says about the voltage or the current through the ammeter or voltmeter. I'm going to draw the two circuits. We don't really necessarily need Ohm's law in order to answer this, but I want you to think about this. There is a relationship, which we'll get to in just a second. There is a relationship between the voltage, the resistance, and the current, and it looks like this. V is equal to I times R, where the voltage across a certain device is equal to its current times its resistance, and the current is the voltage divided by the resistance. That's called Ohm's law, and it describes the relationship between the voltage, the current, and the resistance.
B and U are the same.
Oh yeah, so it's either A, B, or C. All right, I'll stop at 210. Okay, let's see. The current through an ammeter is small. Is that true? Well, it could be true. If you actually have a small current through your resistor, like if the ammeter wasn't there and you had a small current through your resistor, then you still measure that small current through the ammeter. So that's not necessarily true, but it could be true, but not always true, because if the current through the resistor is small, then the current through the ammeter is small. What about the current through a voltmeter is small? This one is not always true. The current through a voltmeter is small. Remember, the voltmeter has a big or small resistance. Has a very, very big resistance. So as those charges come up here, practically none of them are going to go this direction. Almost all of them will go this direction. So it is true, it's necessarily true, that the current through a voltmeter is small. If the current was big through a voltmeter, that would just throw your whole circuit off. It's like the resistor wouldn't even be there anymore. So you want to have a voltmeter in your circuit such that it doesn't really impact the circuit. And you do that by having a high resistance voltmeter. It has a very large shunt resistor, which causes it to draw a very small current. Notice if R is really big, I is really small. So number 2 is necessarily true. What about the voltage across an ammeter is small? Is that necessarily true? It is necessarily true. The reason that it's necessarily true is that you have a very small resistance here. If I have a small resistance, what does that say about the voltage? If R is really, really small, what is V? Big or small? It's very, very small. If R is really, really small, then V is really, really small. So it is necessarily true that the voltage across an ammeter is small. If you're not getting these just yet, that's okay, because when we get into resistor circuits, this will make a little more sense. But in short, we will see a similar rule as we had for capacitors, where the voltages V1 and V2 will have to add up to equal the voltage of the battery. And so the voltage across the resistor in this circuit should be practically the same as the battery. And we'll find that the ammeter has a very, very small voltage, like, tenths or hundreds or thousandths of a volt. So the voltage across the ammeter is necessarily small. It is not necessarily true that the voltage across a voltmeter is small. if the voltage across the resistor is small, the voltage across the voltmeter will be small. If it's big, the voltage will be big here. So that's not necessarily true. So B is the right answer for this one. All right, let's go ahead and define Ohm's law. The flow of charge or current is proportional to the voltage. If a battery provides greater voltage, it provides more energy to the electrons. Remember, voltage is energy per charge. So if my battery gives more voltage, it's just going to provide more energy. So there's a greater flow of current. And so I is proportional to my change in voltage between the batteries. And we're going to see that Ohm's law describes this. Can I go down? Ohm's law describes this relationship based on the resistance. So the resistance is defined as our voltage divided by our current. And that is Ohm's law. It describes the resistance of a device as the voltage over the current. And so if R is big, then a greater voltage is required to provide a current. It's an inverse relationship. So if I have this big, or if this is small, the current, then that means the resistance is big for a given voltage. The unit for the resistance is the ohm. We use the Greek letter omega, capital Omega, for the abbreviation. And usually we see Ohm's law written like this. It's just V is equal to IR. Let's try this quick test just based on Ohm's law and the definition of current. Don't forget your time is in minutes here, but minutes is not the SI unit for time. So be careful of that. All right, let's see. Stop in about 10 seconds. 140, just guess if you're not sure. Okay, I think A is right. I'm going to go and mark it right. All right, so here I first want to find my current. I, by Ohm's law, is V over R. That's going to be 2 divided by 10, which is 0.2 volts. So, or excuse me, 0.2 amps. R, I can think of that as 0.2 coulombs per second. And then if I want to know the total amount of charge, Q, that's going to be the current times time, 0.2 coulombs per second times the number of seconds. 2 minutes is 120 seconds, so that's going to be 240, 24 coulombs. So A is the right answer. Let's see, the next most common was B. Oh, let's see, how did y'all get B? Oh, you multiplied it times, I'm not sure how you got B yet. I guess maybe you multiplied it times 2 minutes in some way. in order to be not converting into seconds. Or you might, sometimes I just multiply all the numbers together in a problem and get the answer. That might know what to do. I'm not sure. Okay. Listen, there's not going to be a whole lot from Chapter 3 on Exam 3. There's maybe one problem from Chapter 3, but Chapter 3 is important as we move into Chapter 4. Let's just do a few clicker questions in the back. Which of these is the correct way to light the light bulb with the battery? Is it A, B, C? Are they all correct, or are none of those correct? If I wanted to light up a light bulb, how would I do it with a battery? All right, I'll stop at 40. 40. A few more seconds. C is right. In order to have a circuit, you have to have a continuous path for current to flow. And so your current starts on the big side, goes here, it goes through my resistor, comes out here, and then comes back to the negative side or the low potential side. So C is the right answer. All these others are incomplete circuits. They don't complete the circuit. You double the voltage across a certain conductor, and you observe that the current increases 3 times. What can you conclude? Is this thing obeying Ohm's law? Is Ohm's law not obeyed, or does it have nothing to do with Ohm's law? We'll see this regarding next time on Wednesday, regarding ohmic versus non-ohmic devices. At 45, I'll stop. 45. Okay, very good. Ohm's law is not obeyed because if I write V equals IR, what I'm saying is that I double the voltage. If I double the voltage, I should get double the current, but what it's saying is I'm getting 3 times the current. So that's saying that Ohm's law is not obeyed. This is called a non-ohmic device. We'll get to that on Wednesday, but it's called a non-ohmic device. Diodes are non-ohmic. Okay, we'll come back to this. We'll just stop there. Y'all have a great day, okay? Get plenty of rest this week, okay? I know it's a tough week, but you need your rest.